Ever wondered why your computer slows down when it's overloaded with tasks? It's a common question, and it might surprise you to learn that there's a specific term for this phenomenon. It's called thrashing, and it's a performance issue that occurs when your operating system becomes so overwhelmed with managing memory that it spends more time swapping pages in and out of physical memory than it does executing actual work. This can severely degrade the efficiency and responsiveness of your system, leading to a situation where little to no productive work is being accomplished. Through the course of this video, we'll be delving into the nitty-gritty of thrashing, exploring its definition, causes, symptoms, how it occurs, and most importantly, how it can be detected and prevented. So if you've ever been frustrated by a sluggish computer and wondered what's going on behind the scenes, you're in the right place. Stay tuned as we unravel the mystery behind your computer's slowdown. So what exactly is thrashing, you may ask? Well, let's break it down. Thrashing is a performance issue that plagues operating systems when they're overloaded with managing memory. In a nutshell, the system is so busy swapping pages in and out of physical memory that it doesn't get enough time to execute actual work. It's like a chef who spends more time washing dishes than actually cooking. This condition severely degrades the efficiency and responsiveness of a system, leading to a situation where little to no productive work is done. Now, let's delve into the causes of thrashing. The first culprit is often insufficient memory. Imagine trying to pack for a month's vacation with only a carry-on suitcase. You'll keep taking items out to fit others in, right? Similarly, when a system doesn't have enough physical memory to meet the demands of all running processes, it results in excessive paging. The second cause is a high degree of multiprogramming. If too many processes are active at the same time, the demand for memory can exceed what is available. This leads to each process getting a minimal fraction of the memory, insufficient for efficient execution. It's like trying to divide one pizza slice between 10 hungry people. The third cause is a poor page replacement strategy. Ineffective page replacement algorithms can exacerbate memory access patterns, leading to frequent page faults and excessive swapping of pages in and out of memory. It's like a librarian who keeps putting books back in the wrong shelves. Lastly, inadequate allocation of frames can also lead to thrashing. If the frame allocation to processes is not managed well, processes may frequently request more pages, which contributes to higher rates of page faults. It's like a warehouse manager who doesn't organize the storage space efficiently, leading to constant shuffling of goods. Now that we understand what thrashing is and what causes it, let's explore its symptoms. How would you know if your system is thrashing? Well, there are several telltale signs. First, you might notice high CPU utilization. This happens because of frequent context switches and the overhead of handling page faults. Despite the CPU being highly active, the actual work done, or throughput, is remarkably low. This discrepancy is a key symptom of thrashing. Secondly, the performance of your system may slow down significantly. Everything seems to take longer than it should, and the overall responsiveness of your system decreases. This is a direct result of the system spending more time on swapping pages in and out of memory than executing actual work. Finally, you may observe an increasing rate of page faults. This rapid escalation indicates that the system is struggling to keep necessary pages in memory, which is a classic sign of thrashing. With these symptoms, we can suspect a thrashing situation. But how does it occur? Thrashing doesn't just happen. It's a process. It's a cycle of events that spirals out of control, causing system inefficiency and a significant drop in performance. So let's delve into the cycle that leads to thrashing, shall we? Imagine a process in your operating system that doesn't have enough frames. This lack of frames results in multiple page faults. For the uninitiated, a page fault is when a process attempts to access a page that isn't currently in physical memory. The system then has to fetch the requested page from the disk, which is a time-consuming operation. Now, the operating system isn't just going to sit idly by when these page faults occur. No, it's going to take action. It says, "Hey, I'm not utilizing my CPU resources efficiently. Let's increase the degree of multiprogramming." So it adds more processes into the mix, thinking it's making the best use of the available CPU resources. But here's where things start to go awry. More processes mean more competition for memory, and with increased competition, each process gets even fewer frames. You can probably see where this is going. The shortage of frames is now even more pronounced. This increased shortage of frames leads to an even higher page fault rate. The system is now spending more time swapping pages in and out of memory than it is executing process instructions. It's like a chef in a kitchen who spends more time looking for ingredients than actually cooking. And so the cycle continues. The system keeps adding more processes to increase CPU utilization, leading to fewer frames per process, which in turn leads to more page faults, and subsequently more time spent on swapping pages. It's a vicious cycle that spirals out of control, leading to the problematic state of thrashing. But all is not lost. Just as a doctor can treat an illness by identifying its symptoms, so too can we address the issue of thrashing. The first step is to understand its occurrence, which we've just done. The next step, this vicious cycle leads to the problematic state of thrashing. But how can we detect and prevent it? Stay tuned to find out. Detecting thrashing early can save your system from a lot of trouble. Let's dive into the methods of detecting and preventing thrashing. One of the first methods we'll discuss is the working set model. This model defines the working set as the total set of pages referenced by a process during a current segment of execution. This concept of a working set helps to encapsulate the memory needs of a process at a given time. By keeping a close eye on the working set sizes of processes, the operating system can adjust the allocation of frames to ensure efficient execution. This proactive adjustment curbs the onset of thrashing, keeping your system running smoothly. Next, we have page fault frequency. This involves monitoring and controlling the rate at which page faults occur. Remember, page faults are situations where the system can't find the data it needs in physical memory and has to fetch it from the slower disk storage. If the page fault frequency exceeds a certain threshold, it's a clear sign that thrashing is on the horizon. The operating system can then take action to reduce the degree of multiprogramming by suspending some processes. This strategy allows the system to regain control over memory management, reducing the risk of thrashing. Moving on to priority adjustment, this method involves reducing the priority of processes that are thrashing or temporarily suspending them. This gives the system a chance to recalibrate and stabilize memory usage. By taming these thrashing processes, the system can ensure that they do not consume too much of the valuable CPU time, thereby preventing the system from spiraling into a thrashing state. Lastly, we have load control. This strategy is about managing the number of processes that are competing for memory. It's like being a good referee in a soccer match. You need to make sure all players are behaving and not crowding out the field. The operating system can delay the initiation of new processes or swap out some of the less critical ones, thereby reducing the overall memory demand. This strategy helps to maintain a balanced load on the system, preventing it from becoming overwhelmed and succumbing to thrashing. In conclusion, detecting and preventing thrashing involves a combination of careful monitoring, strategic allocation, and intelligent control. Each of these strategies, the working set model, page fault frequency, priority adjustment, and load control, contributes to a robust defense against thrashing. So with these strategies, you can detect and prevent thrashing, ensuring your system runs smoothly. And remember, a smooth running system is not just about performance, it's also about maintaining a productive and stress-free environment for all users. Let's quickly recap what we've learned about thrashing. Thrashing is a significant performance issue that occurs when an operating system becomes overwhelmed with memory management, spending more time swapping pages in and out of physical memory than executing actual work. This can occur due to insufficient memory, a high degree of multiprogramming, ineffective page replacement strategies, or inadequate allocation of frames. Symptoms include high CPU utilization, slow system performance, and an increasing page fault rate. The cycle of thrashing begins when a process does not have enough frames, leading to multiple page faults. The operating system tries to compensate by adding more processes, which only increases competition for memory and exacerbates the issue. To detect and prevent thrashing, strategies such as the working set model, page fault frequency monitoring, priority adjustment, and load control can be employed. Remember, understanding thrashing and how to prevent it can make a world of difference in your computer's performance. Thanks for watching.